Let us continue verifying identities, shall we? So I'm taking a look at this problem. And I so quickly start with the left-hand side. But when I do that in my head, now you don't want to do a proof all the way through in your head unless it's the super basic ones. But what I was wanting to do is change this cosine squared of x to 1 minus sine squared of x. And then that could even be factored into 1 minus sine of x and 1 plus sine of x, and then 1 plus sine of x cancel. But that is nowhere near where this is taking me. Okay, so I think in this rare case, I'm going to start with the right-hand side and see what that does. It may be just as horrible. Let's see. So tangent squared of x plus 1 plus tangent of x times secant of x. Okay, now I know that to get to the left-hand side, at some point, I've got to change everything to sine and cosine because that's all that's over here. So I think that's where I'm going to start here. So tangent squared of x we know is sine squared of x over cosine squared of x. So that's the quotient identity, plus 1, we'll deal with him in a minute, plus tangent of x is just sine of x over cosine of x, and then secant of x is 1 over cosine of x. You agree with all that? So we actually use the quotient identity twice for tangent squared of x and for tangent of x. It can even be argued 3 times because we used it twice here, once here, but never mind. Secant of x is 1 over cosine. That's the reciprocal. Now, I don't like you doing more than one thing per line, except in this case where you use, say, quotient and reciprocal, or use quotient or reciprocal a couple of times because they're not interfering with each other. Now, here, check this out. That's a cosine squared of x, right? So I've got 3 fractions that maybe I can combine together, and it might start looking a little more like what we have on the left-hand side over here. So that's what I'm going to do. I'm going to say sine squared of x over cosine squared of x. I'm not touching him. But this 1 over 1 right here, I'm going to rewrite as plus. I'm going to use my unity fraction. So once again, I have some unity fraction action going on right there to try to make that a cosine squared of x denominator. Plus, here, I'm just simplifying. I'm going to multiply sine of x times 1 to get sine of x. And then cosine of x times cosine of x is cosine squared of x. So what did we do? We did unity fraction action, okay? And we also multiplied 2 fractions over here in our third term. Now, when I combine that together, I've got a sine squared plus a cosine squared plus a sine of x. Okay, so I'm not writing what I'm saying. Let me try this again. Hold on. You go right ahead. Now, I've got sine squared of x plus cosine squared of x plus sine of x, okay, over my common denominator of cosine squared of x. Now look, I'm doing pretty good because I got a cosine squared of x right here, and I got a cosine squared of x right here. What else do you see we can do? I think I hear you. I hear you. Pythagorean identity, right? So I got a sine squared of x plus cosine squared of x. That's my most important dude right there. Pythagorean identity. So that's 1 plus sine of x over cosine squared of x. So it's Pythagorean that got me here. Now, check it out. I couldn't give myself full credit for this problem because I don't have an explanation right here. Do you remember what I did from here to here? I just combined it together. It's after we found our common denominator. I just rewrote this out and combined. So you could say combine, or you could say you added, or you could say, you know, common denominator from one step to the other. Just tell me something. Don't leave it blank. If you ever are doing a line and you can't explain what you're doing, more than likely you're not doing something correct. So that's why it's so important that you write an explanation for these lines, even if it's something real simple, like I'm just combining, or like terms or adding. Okay, and a proof. All right, number 8. Okay, we're going to verify the identity. I've got cosine of x over 1 minus sine of x, and that's 1 plus sine of x over cosine of x. What can we do? You know, if we start with the left-hand side, we could split that up into two, the right-hand side, we could split this up into two separate fractions, which does not give us what's on the left-hand side right off the bat. This is one of those problems that if you go down your guidelines, like change everything to sine and cosine, already done. Factor a greatest common factor, nothing there. Find a common denominator, add your fractions together. Well, these are already combined together. There's no adding of fractions going on in this case. Other things that you could possibly do, there's only one left, and that is by multiplying by the conjugate. Not only that, whenever you see the conjugate on the other side of your equation, that's a good sign that multiplying by the conjugate might be the way to go. So I'm just going to start with the left-hand side. So that's cosine of x over 1 minus the sine of x. And then again, I'm going to multiply by the conjugate. Okay, and in this case, it's the conjugate of the denominator. But in every problem, that's not the case. Like if we started with the right-hand side, then you'd be multiplying by the conjugate of the numerator because it shows up on the other side. So I'm going to multiply by 1 plus the sine of x over 1 plus the sine of x. Why are we allowed to do that? Because it's just a unity fraction. Okay, you're always allowed to multiply by a unity fraction. Now, it might not be always something you need to do, but you're always allowed to do that. And because it's just the number 1, but in this case we need to. So I'm going to have to distribute over here. Cosine of x times 1 is cosine of x. Cosine of x times 1 plus the sine of x is cosine of x times the sine of x. Okay, now I'm not saying that we're going to end up leaving it like this. Sometimes you end up distributing and you have to factor it back out. That may be the case here. We'll find out. Denominator, I know I need to multiply out, because the whole reason of multiplying by the conjugate is so you could end up with a square in your problem and use the Pythagorean identity. So I got 1 times 1 is 1. 1 times sine of x is plus sine of x. And then minus sine of x times 1 is minus sine of x. Minus sine of x times sine of x is going to be minus sine squared of x. These two terms cancel each other out. What I did was I used the distributive property twice. I did it in the numerator and the denominator. Conjugates are always going to have these middle terms cancel out when you multiply them together. So I have cosine of x plus cosine of x times sine of x over 1 minus sine squared of x. Okay, now before you jump in right here and change that to cosine squared of x, which it is, look at where we're trying to go. Okay, actually, yeah, here. We're trying to go here. We started with the left-hand side. So we do need to change that, all right, because it's only a cosine down here, so I've got to start somewhere. Let's change that to cosine squared of x. So in the numerator, I still have cosine of x plus cosine of x times sine of x. In the denominator, I have cosine squared of x. And again, Pythagorean is where we're going with that. All right, now that is not what I'm got here, okay, but it sure is close. Notice all this cosine activity going on here. If I factor that cosine of x back out, and I know you're saying, well, it was. Well, you don't always know how you have to leave it unless you can see the whole proof in your head. And I don't encourage trying to see the whole proof in your head, because then you'll get hung up and never finish. You got to write some stuff down. And sometimes you need to distribute, sometimes you don't. There is not a thing wrong with distributing and then factoring your greatest common factor back out, and that would be my explanation, greatest common factor. Now this cosine cancels with one of those, and I'm left with, again, I apologize for the space issue here. Those all go together, okay? So my next line I'm going to write down here, cosine cancels with one of those, and have 1 plus the sine of x divided by the cosine of x. And again, cancel. I just canceled common factors, cosine of x and cosine of x, and we are done with this proof. Okay? Not really all that bad once you know the trick. And that's the argument for practicing as many verify identities as you possibly can. Alright, so we got another identity to verify. It looks like the left-hand side is the more complicated, so I'm going to recopy that. By the way, I don't know if you can hear it, but I'm fighting with a weed eater outside my window. My husband is doing yard work. Yay. But it's a little bit distracting. I apologize. Okay, so I need to find a common denominator and combine these together. So my common denominator is this guy right here, 1 plus cosine of x. So I'm going to multiply by a unity fraction times this 1. So I'm going to multiply by 1 plus the cosine of x over 1 plus the cosine of x. That's all I'm really allowed to do is multiply by a unity fraction minus sine squared of x over 1 plus the cosine of x. So again, I have unity, fraction, action. I'm so proud of that. All right, now, it's a weed eater fight. I got 1 plus the cosine of x minus the sine squared of x over, denominator is 1 plus the cosine of x. Okay, so that's our common denominator. That's why we have this unity fraction stuff going on here. And where does that take me? Is it where I need to be? Let's think about it for a minute. Got a long way to go before we get there. Do you see what we could possibly do? Now, here's one thought. My final answer doesn't have a sine in it. Matter of fact, all it is just a plain old cosine by himself. But somehow I got to get rid of the sine squared. How do you get rid of a sine squared? Oh, easy. Easy, right? Use the Pythagorean identity. But let's go back and write our explanation here. All we did was combine like terms or just add. That's fine if you just say you added. Now, though, I'm going to replace this sine squared. So I've got 1 plus the cosine of x minus, okay? Sine squared is 1 minus cosine squared of x. I cannot encourage you enough to take a look at all 9 of those Pythagorean identities, because you really need all versions of those. You need them in your head, so when you see a sine squared, you know to replace it with 1 minus cosine squared, or vice versa. Now, what people often miss about this problem is they don't use the parentheses, or they don't properly distribute this minus, because you're subtracting sine squared of x. Well, sine squared of x is 1 minus the cosine squared of x. So I'm subtracting this whole thing, which after distributing is going to give me, now watch this, I'm going to change to pink so it won't look such a mess. This is going to be 1 plus the cosine of x minus 1 plus the cosine squared of x over 1 plus the cosine of x. Okay? Now, like term, by the way, again, distribute. That's all I did there. After we used the Pythagorean theorem, I had to, or identity, I had to distribute that minus inside. So now I'm going to add like terms. 1 minus 1 cancels. And I like my polynomials in descending order. So I've got the cosine squared of x I'm going to put first, plus the cosine of x I'm going to put second, over 1 plus the cosine of x in the denominator. Although, I just realized the value of that is not good, because, let's just leave it. It's fine. You'll see what I mean in just a minute. Now, like terms. That's all I did. Alright. Now, how does this turn into just plain old cosine? Well, check it out. Let's factor. Okay, here I have a greatest common factor of cosine of x. So I'm going to factor that out. I got cosine of x times, I pull one of those out, I'm still left with cosine of x plus 1 over 1 plus the cosine of x. So again, greatest common factor. Now, this cosine of x plus 1 cancels with this cosine of x plus 1 to leave me with that lonely cosine of x. It seemed elusive there for a minute, but there it is. We've got it. And what's my explanation here? I cancel common factors. So I'm just going to put cancel. And we are finished with that proof. Alright, let's verify some more. I'm going to start with the left-hand side. I'm going to rewrite it as tangent of theta plus cotangent of theta, all squared. Now, what you cannot do, please don't ever have addition or subtraction with a square on the outside and just tell me each one of those is squared, because that is not what it is at all. What it is it's tangent of theta plus cotangent of theta times tangent of theta plus cotangent of theta. Okay, so I'm just rewriting. That line is really not necessary, but I do want you to see how we get the next line. So in that case, it is necessary. Tangent of theta times tangent of theta is tangent squared of theta. So I'm just using the distributive property. Tangent of theta times cotangent of theta is tangent of theta times cotangent of theta. So is cotangent of theta times tangent of theta, but I'm going to write it in the same order. Now really, I'm using the commutative property of multiplication to rewrite it in this order right here so these match, but just for the sake of space, I'm not going to write that down. Cotangent of theta times cotangent of theta is cotangent squared of theta. So I'm letting you get away with a few little things, okay? But distributive property, that's what that is right there. Okay, now I'm going to combine like terms. These two guys in the middle that I was talking about, the order, changed one of them. We can combine those together. So it's 2 tangent of theta times cotangent of theta plus cotangent squared of theta. So that's just like terms. All right, notice I'm not even looking at the other side. Secant squared of theta plus cosecant squared of theta. We'll get there in a minute. Any thoughts? Any thoughts? Any thoughts? Secant squared of theta is 1 over the cosine squared of theta. Cosecant squared of theta is 1 over the sine squared of theta. We have tangents and cotangents. We got to get rid of those, folks. There's no way to get to these secants and cosecants without reverting to sines and cosines. Unless you use some Pythagorean, you might can use some Pythagorean to change everything. In other words, there's a Pythagorean identity for tangent squared in terms of secant squared, and there's a Pythagorean identity for cosecant squared in terms of cotangent squared. We could go that route, or we can change everything to sine and cosine. It's probably faster if we don't change everything to sine and cosine. What do you think? Why don't you go look up those identities real quick, or reprove them like I did several verify identities ago where we had all 9 listed. But go take a look at them, see what you come up with. So I'm assuming you went and looked them up. Tangent squared of theta is equal to secant squared of theta minus 1 plus 2. Now, you probably already thought about this. Tangent of theta and cotangent of theta have a pretty tight relationship. Tangent of theta times cotangent is 1 over the tangent of theta. That's reciprocal. Plus, and then cotangent squared of theta with a Pythagorean identity is cosecant squared of theta minus 1. Now, I know those are harder to keep up with, that tangent squared of theta is secant squared of theta minus 1 and vice versa. But this is why on the test, I give you a problem that asks you to list all 9 ways you can write the Pythagorean identity, and that way you have it and you can go refer to it like I just asked you to do. Go look at your sheet and tell me what we can substitute. So we did a lot here. I used the Pythagorean identity twice. Okay, I used it here for tangent squared and here for cotangent squared, and I also used the reciprocal for cotangent of theta is 1 over tangent. Now let's write what we have. So I've got secant squared of theta minus 1. Okay, and then let's write that. I don't want to do too much in one line. Plus, those cancel to give me 2 plus cosecant squared of theta minus 1. Okay, so again, cancel. That's what we did. That's what I wrote down. I got a negative 1 plus 2 is 1 minus 1 cancels out. So now I have secant squared of theta plus cosecant squared of theta, and boom, I'm done. Nice. So all I did there was like terms. That was all about the Pythagorean identity and expanding, multiplying and expanding. Right, so here's another identity to verify. Notice we have 2 separate fractions 1 over sine of theta plus cosine of theta added to 1 over sine of theta minus cosine of theta. We've got to be able to combine these together to get the right-hand side. My suggestion is find a common denominator, but let's go ahead and write down the left-hand side equals 1 over sine of theta plus cosine of theta plus 1 over sine of theta minus the cosine of theta. So I'm going to multiply by unity fraction, okay? So this one is going to be this one. So I've got sine of theta minus the cosine of theta over sine of theta minus the cosine of theta, I'm trying to write small, times 1 over the sine of theta plus the cosine of theta. Okay, plus, and I've got this fraction, 1 over the sine of theta minus the cosine of theta times the opposite. So I've got sine of theta plus the cosine of theta over sine of theta plus the cosine of theta. That is a lot of unity fraction action. So unity fractions, plural. All right, now let's combine these together. So my common denominator clearly is sine of theta minus the cosine of theta times sine of theta plus the cosine of theta. In no particular order, okay? I just wrote it because that one's the way it was written for both of them. Actually, numerator I need to distribute. Okay, so now I have sine of theta minus the cosine of theta plus sine of theta plus the cosine of theta. Okay, so we're just combined by adding, but that's what happened after we found a common denominator. Now notice I've got some like terms that are to cancel out. Negative cosine of theta added to plus cosine of theta, gone. And then sine of theta plus sine of theta is 2 sine of theta. Okay, so again, that's like terms. Now I'm starting to look at the other side. I've got the numerator, which is nice. Now how does this turn into sine to the 4th of theta minus the cosine to the 4th of theta? So, you know, when I'm looking at it, makes you nervous a little bit, because when I do sine of theta times sine of theta, it's not going to give me sine of the 4th. But I do know that no matter what, this has to be expanded. Okay? So I'm going to do sine of theta times sine of theta is sine squared of theta. And then sine of theta times cosine of theta plus sine of theta cosine of theta. Okay? Cosine of theta times sine of theta is minus. Now I'm switching the order on you. Commutative property of multiplication, we're allowed to do that. Negative cosine of theta times positive cosine of theta means minus cosine squared of theta. Okay? Alright. Now, combining like terms, these two guys cancel. So I have 2 sine of theta over sine squared of theta minus cosine squared of theta. Now that's close. It looks similar, but we got some force going on here, and we've got squares going on here. We do have the same sign. Okay, so we've got to think about what in the world, and this is one of those where it almost helps to start on the other side of the problem and see if you can't work backwards and meet in the middle. So in a different color, let's go with light blue, because this is not really part of our proof. Let's think about what's going on down here. Okay? So sine of the 4th of theta minus cosine of the 4th of theta. My first thought is let's factor that guy. So that would be sine squared of theta minus cosine squared of theta times sine squared of theta plus cosine squared of theta, right? Because that's just a difference of squares. A difference because it's subtraction. Sine of the 4th of theta is a perfect square. Cosine of the 4th of theta is a perfect square. Look at that compared to what we have down here. So sine squared of theta minus cosine squared of theta. If we could just multiply that by this, can we just multiply that by that? And we can't multiply it on top, too. We're not allowed. So this is not a unity fraction situation. I'm not multiplying the top and the bottom, because if I do, then I won't have my 2 sine of theta anymore. But guess what? That's just equal to 1. right? So I'm totally allowed to just multiply this denominator by this guy right here in blue, but I'm going to put it in green so it matches. I'm going to multiply this guy by sine squared of theta plus cosine squared of theta. How come? Again, because it's just equal to 1. It just makes it look different. It's still the same value, so my final answer, 2 sine of theta over, if we multiply that out, FOIL, you get sine to the 4th of theta minus cosine to the 4th of theta. End of proof. If you wanted to FOIL all that out and show me, you know, but I just ran out of space. And I'm okay with you going straight from there to there because we worked on it in blue up here to show that it was really true. And all we did on that line, don't forget, an explanation for every line is we multiplied. Okay, end of proof. Okay, so to more verify the identities in the review, I'm going to start with the left-hand side. It does appear to be the more complicated one. I'm going to go ahead and warn you, this is a pretty long proof, so I may have a mess of the board here, but I'm going to try to keep it organized. Left-hand side is, I would normally rewrite this, but to save a line of space, okay, your paper, you have plenty of paper, I don't have plenty of space. I'm going to go ahead and change all this to sine and cosine, okay, because that seems to be the thing to do. I'm not telling you it's the fastest way to do this proof, but it's the easiest way, I think, for you to see what's going on. Cotangent, remember that's going to be cosine of x over sine of x minus 5 cosine of x, okay? So all I did was use the quotient identity after I started with the left-hand side. Now, this is telling me that this is a fraction minus a fraction. I need a common denominator. So this is going to be equivalent to cosine of x over cosine of x over sine of x minus 5 cosine of x, and I'm going to multiply that by sine of x over sine of x. So I have a common denominator, okay? And that's a unity fraction that we're doing right there. Okay, so that's equivalent to cosine of x over, all right, now I'm going to write this as one fraction. So I've got cosine of x minus 5 cosine of x times sine of x over my common denominator of sine of x. Now I know that looks terrible. This is a complex fraction. What I want to do is I'm dividing by this big fraction in the denominator, so I'm going to invert and multiply. Okay, so the explanation here, by the way, is I'm just combining or add or subtract fractions to get, I had a common denominator, combined it together. Now I'm going to invert and multiply. So this cosine of x stays on top. It's really cosine of x over 1 times, I'm flipping this guy, so this is sine of x over, this is cosine of x minus 5 cosine of x times the sine of x. Okay, so again, invert and multiply, or you could call that dividing by fractions, whatever you want to call it. Remember, this is really over 1. Now I need to stop and look. Please don't cancel this sine of x and this sine of x. You can't do that, okay? And here, if you do, well, first of all, it's wrong, but even if you split it up, it takes you right back where you started, okay? So it's going in the wrong direction, even if you do it correctly. What we want to do is maybe factor out this common cosine of x here and cancel it with that guy. So I have cosine of x times sine of x remains in the numerator. I'm factoring out this common cosine of x. That's going to leave me with 1 minus 5 sine of x. Now I can cancel this cosine and this cosine. But what we did was factor a greatest common factor. Okay, so now my next line is canceling. So now I have sine of x over 1 minus 5 sine of x. Okay, and again, the step that got me there was canceling that common cosine of x. Now look, it's sort of like my answer, but not. My answer on the right-hand side has cosecants in it. This has two different terms of sine in it. What do I do? What do I do? Well, I can turn sine into cosecant, right, by using the reciprocal property. So that's exactly what I'm going to do. And see if it'll take me closer to that answer. So the reciprocal of sine of x is 1 over cosecant. So I'm going to rewrite this as 1 over the cosecant of x. That is my numerator, okay? And then in the denominator, y'all, I'm not liking that. Hold on. This is just ugly. Okay, let me try this again. All right, so this is going to be 1 over the cosecant of x divided by 1 minus 5. I'm going to do the same thing with this one. That's going to be times 1 over the cosecant of x. And again, it uses the reciprocal twice. Here is 1 over cosecant, and here 1 over cosecant. Now here I am again. I need a common denominator in the denominator here. Okay, so numerator, I'm not messing with him. 1 over cosecant of x. Denominator, I'm going to multiply this guy by a unity fraction, cosecant of x over cosecant of x. So that gives me cosecant of x over cosecant of x, of course, times that 1, minus 5 over cosecant of x. Again, unity fraction, or I would take common denominator as your explanation there. Hopefully we're almost finished. Okay, so here I've got cosecant of x minus 5 over cosecant of x. That's looking promising, right? What did I do there? I just combine after finding my common denominator. Now I invert and multiply. So I have 1 over the cosecant of x, that's my numerator, times flip this guy, cosecant of x over cosecant of x minus 5. Cosecants cancel. Okay, so again, invert, and multiply. Okay, cosecants cancel, so I get 1 over cosecant of x minus 5. And then I'm just relieved. This is when that filling in that rectangle is like, whew, thank goodness, almost didn't get there. Cosecants cancel. So that was the line explanation for that. There's a reason that was the 12th one, and there's still another one after this one. I know this video is like super long, but it is a review. You don't have to watch every one of them. You can skip, and I wanted to keep all the verify identities as close together as possible. So this is the last verify identity on this video, and then part 3 video starts with other problems not verifying the identities. It goes to some difference. So I'm going to start with a side. I don't know, what side do you want to start with? Left-hand side, right-hand side? They both look reasonably complicated. If I start with the left-hand side, the what to do gets a little lost. There are no squares, so there's no using the Pythagorean identity. Don't cancel those cosines, because that's not right. You can't cancel part of a sum or an addition, so don't do that. This is one of those problems that's asking you to go ahead and multiply by conjugate. Okay, conjugate of what? The top or the bottom? I don't know. Let's just pick one. Usually when I multiply by conjugate, it's for the denominator. So let's just multiply and see what happens. Again, this is one of those try somethings. To the point where I think even starting with the left-hand side might even be smarter to figure out what to do. Let's just try that. Okay, let's try something. I may even start this video over because this isn't going to work very well. Let's just see what we can do with it. So, I'm going to multiply by the conjugate. Okay, so there's my left-hand side equals. So, I'm going to say 1 minus the cosine of x over 1 plus the cosine of x. And the conjugate of the denominator, I'm just picking 1 minus the cosine of x over 1 minus the cosine of x. Okay, so that is a unity fraction. That's why we are allowed to do that. Why would we do such a thing? Because we need to do something. I don't know what to do with it, so I'm going to just try something. And again, I picked the denominator. It could have just as easily been the numerator, and maybe both of them will get us there. We're just trying something. So in the numerator, I'm going to FOIL. 1 times 1 is 1 In other words, the distributive property. 1 times negative cosine of x is that, negative cosine of x. Negative cosine of x times 1 is another negative cosine of x. And negative cosine of x times negative cosine of x plus cosine squared of x. In the denominator, I have 1 times 1 is 1. 1 times negative cosine of x is negative cosine of x. Positive cosine of x times 1 is plus the cosine of x. And cosine of x times negative cosine of x is negative cosine squared of x. Okay, so distributive property. Alright, now in the numerator, nothing cancels out. We're just adding like terms. So I got 1 minus 2 cosine of x plus cosine squared of x. In the denominator, those terms cancel and I get 1 minus cosine squared of x. Now, typically, when you multiply by a conjugate, it's so you'll have a square, and you can change that using the Pythagorean identity. So that is sine squared of x. The question is, do I actually want to replace that with sine squared of x? Would that do me any good? I don't know. I'm looking at the right-hand side over here. Cosecant of x is 1 over sine of x. Cotangent of x is cosine of x over sine of x. I'm feeling pretty good about changing it because both of these denominators are sine of x. So I think we're on the right path anyway. But we didn't write an explanation for this line. It was called like terms. We'll see if I can squeeze another line down here. So I have 1 minus 2 cosine of x plus, hard to read, cosine squared of x over, using the Pythagorean identity, sine squared of x. Okay? So, I'm looking at this, and I'm thinking, how can I get from here up to here? Okay. So I'm thinking, look, this numerator right here, and this is what happens, by the way, is you look at these and you get stumped, you don't know where to go. That makes me think of a trinomial to the point where I want to rewrite it. Maybe like cosine squared of x first, minus 2 cosine of x next, and then plus 1 over sine squared of x. Are we allowed to do that? I mean, are we allowed to rearrange? Sure you are. It's the commutative property of addition. I'm just going to put commute. Totally allowed. So then, I don't know, it makes me want to factor it because you've got something squared minus 2 times that same something plus 1. In other words, what multiplies to be 1 and adds to be negative 2, just like a regular old trinomial, and that's a negative 1 and a negative 1. So normally that'd be like x minus 1 times x minus 1. So here's what I want you to think about. What you're really factoring is like x squared minus 2x plus 1. You know, that factors into x minus 1 times x minus 1. We have the same problem, but we have a cosine of x everywhere there's an x. So that's going to be cosine of x minus 1 times cosine of x minus 1. And that's actually what we had to start with, but I rearranged the order. Okay, so anyway, that's over sine squared of x. Now that might be something because look, we have a cosine of x minus 1 and a cosine of x minus 1 over a sine of x. By the way, we factored here. Don't forget your explanation. And it's factoring the trinomial. There's 2 sine of x's, so I could say that's cosine of x minus 1 over sine of x times cosine of x minus 1 over sine of x. Why would I do that? Because this is all squared, so that's really cosine of x minus 1 over sine of x squared, so it gives me my square on the outside, but this is this. Yeah, it is, right? Because I have cosine of x over sine of x minus 1 over sine of x, all squared. That gives me, this guy right here is cotangent of x minus this guy right here is cosecant of x squared. Now look, I've done all these lines because I was getting carried away. But let's write an explanation. Remember, we factored. And we just split up our two factors. Here we rewrite this is square. It's like weird little things we're doing here. Now, we split the fraction again. But this time with addition and subtraction. Okay. Here we use the quotient. And we use the reciprocal. Alright, now look. This is still not what we need. Look how it's backwards. Well, what do I do to get it flipped around like what I need? Well, first of all, when you square something, it doesn't matter what order it's in, it turns positive. So there's really no difference between cotangent of x minus cosecant of x or cosecant of x minus cotangent of x. Now again, I'm not saying you can always flip or reverse the order of subtraction. I'm saying when you square it, you can, because things that are squared are always positive. But a way to show this would be maybe to factor out a negative. So watch this. So I've got negative, okay. That's going to make that a negative cotangent of x. It's going to make that a plus cosecant of x, right? Squared. This line is identical to this line. If I distribute that negative back inside, and then when you square, so I'm factoring a greatest common factor of a negative. When you square this negative right here, negative to the second power, means this is just negative. It goes away, cotangent of x plus cosecant of x. Again, this is just a formal way of expressing the fact that when you square a negative, it turns positive, because we do the negative squared, which is what we have if we change the order. I'm going to finish this guy up here in pink. I'm frustrated because I'm short a line. I rearrange the order right here. That's going to give me cosecant of x minus cotangent of x, all squared. Okay, and that's the commutative property of addition. And that is the end of my proof. Okay, down here I didn't write an explanation of that, but you square the negative. Okay, and that turns positive, so it disappears. That one's fun. That's why it was last.